Hello, everyone. This is Derivation Dudes. I'm one of your hosts, Noble H. Tech, and today we are going to prove that the Directrix focus definition and the focus definitions of an ellipse and a hyperbola are equivalent. I mentioned this in my last video, but I mentioned this very vaguely. Really, I should have done this video first in order to introduce you to these two definitions. And we're not just going to introduce you to these two definitions, I'm going to prove that they're equivalent. First, I'm going to introduce you to the definition. One definition of an ellipse is focus and directrix. You have a focus, and then you have a directrix. And every point on this ellipse is such that if you draw a line between the focus and the point, and then you draw a line between the point and the directrix, C over A, that ratio is less than 1 and is a constant for every single point on the ellipse. So, if you remember parabola, the definition for parabola also has a focus and directrix. But in that definition, the ratio is exactly 1. In this definition, it's a little different. The ratio is less than 1. So yeah. In hyperbola, it's the exact same, but it's greater than 1. So if you have a focus and you have the directrix, then you draw a line between the focus and then the point. Draw a line between the point and the line. C1 over A1 is greater than 1. It's very clear here because we have C2 and then we have A2. Clearly C2 is longer than A2, so the ratio is greater than 1. So that's for a hyperbola. Again, C1 over A1 equals C2 over A2. It's the same for every point on the hyperbola. The ratio is always greater than 1 for a hyperbola, less than 1 for ellipse. This is the new definition. The old definition, not the new definition, the definition that you haven't learned in school. The definition that you have learned in school is this one. You have two focus, for an ellipse, you take the sum of the distances, and then that sum of distances is constant. I'm not going to explain this because I'm going to assume you already knew this for school. But basically, here's the new part. In school, you learn that the eccentricity, you have a center, you draw a distance between center and focus, that's called C. You have a center, you draw a distance between center and the edge of the major axis, that's called A. C over A is the eccentricity. That's what you learn in school. Here is an equivalent definition of the eccentricity. You take the distances between the focus, F, or in school, you learn this as 2C. And then you take the sum of the distances, D1 plus D2. I'm going to call that D. In school, you learn that the sum of the distances is 2A. So this is 2C over 2A. So F over D. So the reason I'm using this definition is because it'll just make things simpler for us. We don't need to deal with a center. In school, you learn C over A. In this definition, it's 2C over 2A, where 2C is called F and 2A is called D. So hopefully you see how those are equivalent. In this definition, it's the same, except it's the differences of distances. Again, I'm not going to explain this because hopefully you learned this in school. But basically, I'm going to say D2 minus D1 here. I'm going to say that's D. In school, you learn that's 2A. I'm calling it D. And the distance between the focus. In school, you learn that's 2C. I'm calling it F. So in school, you learn the eccentricity is C over A. I'm going to say it's 2C over 2A. Or F over D. Okay. So how do I prove that these definitions are equivalent? Well, we need to prove two things are equivalent. First, we make an equation for the first equation and an equation for the second equation. We need to prove those equations are equivalent. Then, we need to prove the eccentricities for each equation are equivalent. So we take the first definition and make an equation out of it. We're going to say the focus is AB, and the directrix is AX plus BY plus C, equals 0. The distance to the focus is square root x minus a squared plus y minus b squared, distance formula. Distance to the line is this formula, ax plus by plus c, all over square root a squared plus b squared. This is a formula you probably learned in pre-calc. We're probably going to do a derivation of this later, but for now, just accept it. But however, we can divide both sides by squared a squared plus b squared. On this side you get 0. On this side you get another ax plus by plus c thing. So we just say that squared a squared plus b squared equals 1, and we get rid of the denominator. This is the first trick we use in this proof. We say that this equals 1. This is valid. I want you to convince yourself that this is valid by writing down a directrix and then trying to get another form of that directrix where square root a squared plus b squared equals 1. It can be done for any line. I'm going to maybe you can experiment with that, But if you need me to explain it in the comments, I will. But you have to accept that square root a squared plus b squared can equal 1. That is going to make it this so much simpler. Then we say ratio of distance from the distance to the point, distance formula, over x plus 3y plus c, which is the distance to the line. The added ratio is the eccentricity. We're going to call it e. Multiply both sides by the denominator. We have squared x minus a squared plus y minus b squared equals e absolute value was ax plus by plus c. Square both sides. First, I distribute the e on the right side, so it's eax plus eby plus ec, all squared, and then on the left side we get rid of the radical. Now, this is kind of the complicated part, the first complicated part. But we say that the e, and then we use another trick. E equals e times squared a squared plus b squared. The reason we say that is because squared a squared plus b squared equals 1. And then we distribute the e. So it's squared ea squared plus eb squared. That's the coefficient of x squared plus the coefficient of y squared. And then you square root the sum. That's the eccentricity for the first definition. So we have an equation for the first definition and eccentricity for the first definition. Now we do this for the second definition. For the second definition, we have one focus AB, the other is CD, squared x minus a squared plus y minus b squared plus squared x minus c squared plus y minus c squared equals d. Plus is for ellipse. However, for hyperbola, it's minus. So I want to say plus or minus. That equals d. Okay. However, we want to find the eccentricity, so we can prove that they're equal at the end. So f equals the distance between the foci, which is square root a minus c squared plus b minus d squared. Square both sides, f squared equals a minus c squared plus b minus d squared. Divide both sides by d squared. The reason I did that is to get f over d whole squared equals a minus c over d squared plus b minus c over d whole squared. F over d is e, so we take the square root of both sides, and now the right side, square root a minus c over d squared plus b minus c over d squared. That is the eccentricity. So you have the eccentricity for the second equation, we have the equation for the second equation, and then we have the same for the first and the equation. So we're going to turn the second equation into the first equation. This is where it gets complicated. So I need you to stay with me. If you have any questions, please leave them in the comments. Square both sides of the equation. You get x minus a squared plus y minus b squared. That's this squared. Plus x minus c squared plus y minus c squared. That's this squared. And then you take plus or minus 2 times the product. So it's this times this. Again, I want you to see the connection. And then I put a 2 in front because that's how squares work. Okay? And then the right side is just d squared. So again, we have a kind of long expression here. Okay? Get the radicand alone. So subtract both sides by d squared, we have minus c squared on the left side. Subtract both sides by the radicand, we have minus or plus on the right side. Now, we want to get rid of that minus or plus, because that's going to be a real pain to keep track of. Square both sides. Minus or plus squared 2 becomes just plus 4, since negative squared is positive, positive squared is positive, and then on the right side we get rid of the square root. Now on the left side, things get complicated. Okay, so first I'm going to break this up. I'm going to break it up into x minus a squared plus y minus b squared plus x minus c squared plus y minus d squared, and I'm going to square that. First, we're going to focus on that. Now, for x minus a squared plus y minus b squared, I'm going to say that is 1 unit, and x minus c squared plus y minus d squared, I'm going to say that is another unit. So that squared, x minus a squared plus y minus b squared, squared, plus x minus c squared plus y minus d squared, squared, plus 2 x minus a squared plus y minus b squared squared, x minus c squared plus y minus c squared. That is the product and 2. So remember, it's square plus 2 times product. That's how squares work. And then now we figured out that unit squared. Our other unit is minus d squared. So we square minus d squared to get positive d to the 4th. And then it's minus 2 times the product, because it's subtraction, so it's minus. So minus 2d squared times x minus a squared plus y minus b squared plus x minus c squared plus y minus d squared. How did I know to break it up like that? I didn't. It took me about 15 minutes to figure that out. So that's the first real trick in this proof. I need you to figure out that step. I need to figure out how that works. Hopefully you accept that. We're moving on to the next step. Okay. Now, we realize that we have x minus a squared plus y minus b squared times x minus c squared plus y minus c squared on both sides. Here it's plus 2, here it's plus 4. So subtract both sides by the plus 4 version. On the right side, we get 4 minus 4 equals 0. On the left side, we get 2 minus 4 is negative 2. So now, you notice we have square plus square minus 2 times the product. This is the same as the difference squared. So what we can do is that we say it's x minus a squared plus y minus b squared minus x minus c squared minus y minus d squared. Whole squared. However, we can also switch it. So it becomes x minus c squared plus y minus d squared minus x minus a squared minus y minus b squared. In the first version, I said a and b came first. In the second version, I said c and d came first. We need to realize this so that things will go right in the end. And I'll point this out to you at the end. And then we have that squared, and then I just rearrange things. So d to the fourth comes out front, and then I put the minus 2d squared in the middle. Now, we almost have a perfect square here, because we have this squared plus this squared minus 2 times the product, except the product isn't correct, because remember, this unit is x minus c squared plus y minus d squared minus x minus a squared minus y minus b squared. Here, the signs of x minus a squared and y minus b squared is plus 1. So I need you to notice that difference between this and this. It's a very subtle difference. So we want to get the sign from plus 1 to minus 1. How do we do that? We break the plus 1 into minus 1 and plus 2. So I need you to realize minus 1 plus 2 equals plus 1. So that's what we're going to do here. So I changed the signs, so it's x minus c squared plus y minus c squared. That stayed the same. That's plus 1 from this term to this term. And from this term to this term, it's minus 1. And in order to counteract that, I added a plus 2 term. So in this term, it has plus 2 x minus a squared plus 2 y minus b squared. So I need you to realize that the minus 1 plus 2, they counteract to the same thing. So now we have the perfect square we want. We have something squared plus something squared minus 2 times the product. We need to get rid of this term, so I'm going to add it to both sides. Okay, so now we have all of the terms we want of the square on this side, and then the term we didn't want on the right side. So on the left side, we use that identity. We say that this is one unit, x minus c squared plus y minus c squared minus x minus a squared minus y minus b squared. I'm going to put that out front, just because it'll make things easier for us. And then I'm going to say minus d squared is the other unit. So it's the difference of x minus c squared minus plus y minus d squared minus x minus a squared minus y minus b squared. That's one unit, and it's the difference of that unit and d squared. So that's what I did here. That squared equals this. Okay, so all I did was contract the left side a little. And then here we have 2x minus a squared plus 2y minus b squared. We factor out the 2, so we get 2 times 2d squared. That is the same as 4d squared, x minus a squared plus y minus b squared. On the right side, I just factored out the 2. That's the easy part. Okay, I'm going to keep moving. Now, on the left side, we have this kind of square minus square plus square minus square minus square. We need to simplify this. The way I'm going to simplify this is just expanding it out. So on paper, you can just expand the x minus c squared all out into x squared minus 2cx plus c squared, and then you can expand this out into minus x squared plus 2ax minus a squared. And then I'm going to let you do that on your own, since that's just simplifying. But basically, we get 2a minus cx plus c squared minus a squared. And then for the y's, we get 2b minus cy plus d squared minus b squared. And then the minus d squared just stays the same. Okay, I'm gonna let you do that on your own paper because you need to because that's the easy part in this proof. So I can't show every step. So I need you to do that on your own. So 4d squared is 2d whole squared, and then that's another easy step. So this is the easy step. I know it looks hard because I've changed a lot of things here, but this is really just simplifying things a little. There's no check here. And then we divide both sides by d squared. The reason I did that is to get x minus a squared plus y minus b squared on the right side alone. So 2a minus c divided by 2d, the 2's cancel out, a minus c over d, and then 2b minus d all over 2d, 2's cancel out, b minus c over d, y. Okay, we have the x term, the y term. Everything else we're going to say is a constant. So we lump it all together, c squared minus a squared plus c squared minus b squared minus c squared, lump it all together, all over 2d. So now we have this on the right side. That's the same thing we have on the left side here. So we've done it. We've transformed the second equation into the form of the first equation. Now you're wondering, well, why did we make the switch at the beginning? I mean, at the middle. Why did we say that it's x minus c squared plus y minus t squared minus x minus a squared minus y minus b squared? The reason I made that switch is because if I hadn't made that switch, then follow all of the steps except me not making that switch. Follow all of the steps what I did except me not making that switch. If you do that out on your own, you will get C and D on the right side over here. That's not what I wanted. I wanted A and B, just to emphasize that it was in the same form as A and B over here. So that's why I made that little tiny switch, just to make things a little more clear. So that's I just want to emphasize that that's the kind of little detail you have to pay attention to in these proofs, because little details like that can change to little things that just make things more unclear. So now just to make this even more clear, I'm going to switch the sides. So we have x minus c squared plus y minus b squared equals something times x plus something times y plus a constant squared. Again, I just want to go back to the first equation just to emphasize that this is in the same form. It's x minus a squared plus y minus b squared equals something times x plus something times y plus a constant squared. So that's what I did here. Now it's in the same form. Now we still need to check the eccentricities. So in the first equation, according to the first equation, we said that it was the square root of the sum of the squares of the coefficient of x and the coefficient of y. So take the coefficient of x, square root, plus coefficient of y, square root that. That's what I'm going to do here. So square coefficient of x, a minus c over d squared. Square coefficient of y, b minus d over d squared. Plus square root it all. Now according to the second equation, it is square root open parentheses a minus c over d squared plus b minus d over d squared. Yeah. So we have to realize, according to the second equation, we have that. According to the first equation, we have that. So they're equal. So we have the same eccentricity and same equation form. So that means these two definitions are equal. We are done. So yeah. One of the surprising things in this proofs is that the plus or minus goes away once you square both sides. So we never needed to keep track of these things. So once you put that the eccentricities are equal and that the form of the equation is equal, we don't need to do like different cases for ellipses and hyperbolas. So it converges to the same case because we got rid of the plus or minus. So that's one of the really convenient things about this proof. Everything else is extremely inconvenient. It took me hours to get from here to here. It took me hours of work and trick and to just to figure out how we do all of this using algebra. But it works, and we do it all using our precalc knowledge, which is one of the beautiful things about this proof. We solved this very complicated problem of two. I mean, really, look, we have these very two abstract definitions. We have a focus on Directrix, and then here we have the school definition, which is two foci. And then we need to make these equations out of it. And then if you compare the equations, we have something squared plus something squared equals something squared on here. And then for the second definition, we have square root plus or minus square root here. So these very two different equations. I just wanted to show you how different these are. And they come out to the same form using all of this algebra. But all of this algebra, I didn't use some calculus trick here. It's just all algebra. It's just all pre-calc. Again, I'm going to link to this in the description. Hopefully you followed all of this. If you didn't, please ask questions about what you didn't follow. But I just really want to emphasize that this is all pre-calc, everyone. This very complicated proof, this very long proof, is a very long pre-calculus proof, and it works. And I'm just very proud of this proof, personally, because I made it myself. I could not find it on the internet. I really hope this proof helps you in showing you that the focus directrix definition and the focus definition are the same. If you have any questions, again, just comment. I will be happy to explain, because I do think, even though I went, you know, even though it's a very long proof and it's probably going to be a very long video, I think I went a little too fast. And yeah, we did it. And yeah, this is probably like the longest proof I've ever written. It's probably about like 5 pages, really. So I really hope you appreciate this proof, that these two definitions really are equivalent, because I could not find a proof of this online. And yeah, have fun doing math. Have fun doing algebra. Have fun doing proofs. Have fun reading this proof. And yeah.